Okay, in this video we're going to talk about inverse functions. I'll show you how to find an inverse graphically and algebraically. We'll talk about the distinction between a one-to-one function and a many-to-one function. And then I'll show you how you can use composition to determine whether or not two functions are inverses. Before we do our first example, some definitions. Of course, the definition of a function. It's a mapping where for every x there is exactly one y. A one-to-one function is a mapping where this xy pairing is perfectly unique. There's one x for every y, one y for every x. This ordered pair, they happen to be perfect for each other. We call it one-to-one. And then what it means to be the inverse function of f. We say if f is one-to-one, the inverse of f, we'll use the notation seen right there. It looks like f to the -1 power, but it's actually f inverse. It's the function with a domain of R and a range of D. So it's the function that switches the domain and range and switches the inputs and outputs in such a way that this statement at the bottom is true. Our first example. Let's find an inverse graphically. So if an inverse is simply switching the domains and the range, switching the x and the y, then I can make a table here where I switch my ordered pairs. I'll call this x and I'll call this f inverse. And if we switch 1, 1, well, we still have 1, 1. But we'll have 0, 2 instead of 2, 0. We'll have 2, 3 instead of 3, 2, and -1, 4, and 3, 5. And then if we go and plot these new points, I'll just put a circle around this one. In fact, I'll use circles to plot all those points. 0, 2 would be right here, and 2, 3, that would be right there, and -1, 4, that would be right here, and 3, 5, it would be right about there. So we see this graph that looks like this. And this is the inverse of f. And what is that graph really? What did we just do? Well, we successfully mirrored the original function over the line y equals x. And basically that is the graphical representation of an inverse. It's the mirroring over the line y equals x, because if you switch x and y to yx, well, you just flip it over that line. I will point out here, before we go forward, the domain of the original was from 1 to 5, and the range of the original was from -1 to 3. Meanwhile, in our inverse, the domain was from -1 to 3, and the range was from 1 to 5. One last thing that I'll point out, the inverse is not a function. As we can see, it doesn't pass the vertical line test. A quick way to tell whether or not a function will have an inverse that's also a function is, instead of the vertical line test, we check a horizontal line. You can see that a horizontal line passes through my original function multiple times. That lets me know that its inverse will not be a function, because the vertical line test will fail. Example 2. Let's find some inverses algebraically. Do two parts actually, because one's a very standard way and the other's maybe a little bit more algebra involved. So basically what we do is we switch x and y, and it's usually easier to rewrite f of x using y first. It's a simpler notation to use. So you switch x and y, and then you attempt to solve for y. If you can successfully solve for y, if it can be done, then that means that it does have an inverse that is a function. So to solve this equation, I need to isolate the cube root. So I've got x minus 2 equals the cube root of y minus 7. Now with the cube root isolated, I can cube both sides of the equation, of course giving me just y minus 7 on the left and x minus 2 cubed on the right. And if I rewrite this with y on the left-hand side, this would be y equals x minus 2 cubed plus 7. And the last step that you should try to remember to do is rewrite that y as f's inverse, because what we were showing then is that our function f has an inverse that's also a function. Letter B, this is one that sometimes students seem to think can't be done, because when you first switch x and y, it seems sort of hopeless because you have an instance of y in the numerator, you have an instance of y in the denominator, and how are you going to solve for that y? Well, here's the trick. Basically, multiply both sides by y minus 3, and then distribute the x. It seems like things are getting worse. Sometimes in math, things get worse before they get better. So here we go. Distributed the x, and now I see two terms that have a y in them, and I'm trying to isolate y. So I'll group those together on the left side of the equation. That'll give me xy minus 4y on the left, because that'll be a minus, and I want that 3x over there on the right. That equals 3x plus 1. Factor out your y. That was why you isolated the terms with the y, so you can pull it out, and you can sort of see your way out of it from here, dividing both sides by x minus 4 will give us y all by itself on the left side of the equation. So that is f's inverse. One more thing about that particular example. You'll notice the very first step, the domain x could not be equal to 3 because that would create a divide by 0 error in the denominator. Likewise, the range y could not be equal to 4. I can tell that by looking at the major terms, the terms with the highest degree in the numerator and denominator, and dividing them. 4x divided by x makes 4. Meanwhile, in my result here, the domain x can't be 4, and the range y can't be 3. So domains and ranges switch. In the next example, I just want to discuss this difference between one-to-one and many-to-one. The idea of a one-to-one function is that each x has exactly one y, but that pairing is also unique the other direction. Each y has exactly one x. A one-to-one function will pass the horizontal line test, or ham, lettuce, and tomato test, whatever it might be. So in order to be a function, it must pass the vertical line test, where you can pass a vertical line through it and it only intersects at one point. In order to be a one-to-one function, it also passes the horizontal line test. And you can see that our first picture here, this one is 1, 2, 1. The next two, well, here's a parabola, and we can see that that does not pass the horizontal line test, and this other curve also does not pass the horizontal line test. These are called many-to-one, and it's good to know when you have a many-to-one function, because sometimes you will be asked to find a domain on which that function is one-to-one. So if you just imagine taking your scissors out, I had a pair handy here. If you imagine snipping that parabola right there at its vertex, and making a little cut here, and only looking at, say, the right-hand side of that parabola, or the left-hand side, you pick, but I'm going to pick the right-hand side. On that domain, looks like from 1 all the way up to infinity, the parabola is a one-to-one function. And that's important because one-to-one functions is what we need for solving. This other curve we have here, think about where to cut. Right? Is there a place you can make a cut so that it is a one-to-one function, but it also maintains the range of the function? And you can imagine making a little cut right here and a little cut right here. And you'd still have the entire range of the function, but it would pass the horizontal line test everywhere in between. In our last example here, I asked which of the following functions are inverses of each other. And one way, I should put that on the screen, one way that you could answer this question is switch x and y and solve. Maybe do it again here, however many times you have to do it, and to say, oh, those actually are inverses. But we also could use the rule of composition, which says that if f and g are inverses, then f of g of x will equal x for all x in g's domain. I could say it the other way too. G of f of x will equal x for all f in G's domain. That's, I should clarify, that's if f and G are inverses, or f and h, or G and h. So if I wanted to do that test here, I could check these two, and then maybe check these two, and maybe check these two. So let's see what it would look like comparing A and B. F of G of x. That means to input the function g into f. So 3x minus 4 over x minus 2. All right. Now I follow my function rule here for inputs. Twice the input over the input minus 3. So in the numerator, I've got twice the input, so 2 times 3x minus 4 over x minus 2. And then in the denominator, the input minus 3, 3x minus 4 over x minus 2 minus 3. Okay, we want to know if this equals the identity, if it just equals x. So we have to do a little algebra. The algebra you should do is clear those fractions. Multiply by x minus 2 over x minus 2. That'll cancel the x minus 2 in the denominator there, leaving 2 times the quantity 3x minus 4 over. Now down here, the x minus 2 will clear that fraction and get multiplied by the 3 there. So we have 3x minus 4, the denominator canceled, minus 3 times the quantity x minus 2. Okay, one more step and we'll know whether or not these are inverses. In the numerator, I've got 6x minus 8 over, and in the denominator, I've got 3x minus 3x is 0, and negative 4 plus 6 is 2. 6x minus 8 over 2 makes 3x minus 4. Therefore, they are not inverses because we didn't just get plain old x. Alright, since the bell's ringing, I'll leave it up to you to figure out whether f and h are inverses or g and h are inverses. One pair is, the other pair isn't.